And welcome to the morning session. It's a real great pleasure to have Matt Headrick here, and he's going to tell us about QI aspects of AdS CFT. This is the first of his set of 3 lectures. So Matt, please.
Okay. So thank you, Onkar, and to the other organizers for inviting me. It's always great to come to ICTS. And thanks to yesterday's lectures, there are a lot of connections between what I'll talk about today and what we heard about yesterday. So I'd like to thank them for setting me up nicely. Although if I seem unprepared, that's also their fault, because I was going to spend the afternoon preparing my lectures, but then the talks were so good that I just ended up paying attention to them instead. So Onkar gave me the job of talking about QI aspects of AdS CFT. I guess anticipating that I would have several years of lectures to give, which is what it would take to cover all the QI aspects of AdS CFT that we've discovered in the last 20 years or so. But it turns out I only have 3 1.5-hour lectures, so I have to pick and choose. And so I'm really just going to focus on one QI aspect of, I need a more dramatic color, of AdS CFT, which is entanglement entropy, which is already something that contains a huge amount of physics. More than enough to fill up 3 1.5-hour lectures, as we'll see. And so there's a lot of QI aspects that I won't talk about, some of which were touched on yesterday. For example, Pawel was talking about chaos. He was talking about complexity. Which is also related to scrambling. I'm just throwing out buzzwords to mention things that I won't be talking about, but that are quantum information aspects of AdS CFT. There's many others, for example, quantum error correction, tensor networks, and so on and so forth. They're all actually closely related to entanglement entropy, and entanglement entropy is the thing that kickstarted this idea of or is one of the things that kickstarted the idea of trying to understand information in the context of AdS CFT. The other thing, of course, being the black hole information paradox, which is actually closely related to entanglement entropy, and we'll see if I get that far in the lectures today. Why am I focusing on this as opposed to the other things? I think it's a good starting point, partly because the notion of entropy is hopefully already familiar to anyone with a degree in physics, basically. So you don't need that much background knowledge to understand what the questions are. But also, for me, it provides one of the sharpest connections between information and geometry, information and space-time geometry that we know. So space-time geometry being essentially what encodes the physics of gravity. And it's been known since the days of Bekenstein and Hawking that there's some connection here, and the connection goes via entropy, okay, via the Bekenstein-Hawking formula. And what we have that's new, so Bekenstein-Hawking formula dates back 50 years. AdS CFT dates back 25 years or so. And so what we have that's new, the new thing in this is a generalization of Bekenstein-Hawking formula, which is the Ryu-Takayanagi formula. So this connection here is via this formula that was discovered almost 20 years ago, and which is going to be the main topic of my talks, okay? And there's so much to say about this formula that one can go on and on about it, okay? But although I said that one can understand the questions from a basic understanding of entropy, it is true that there's a certain amount of background material. And so actually, probably most or maybe all of this lecture will be on background material. We'll see if we get to Ryu-Takayanagi or not. And the background material has to do with entropy and entanglement entropy. That's one thing. and then the application of those concepts in quantum field theory. And that second thing is necessary because in AdS-CFT, as we see on the right-hand side of the slash, we have a quantum field theory. And so one has to understand the idea of entanglement entropy in a quantum field theory in order to appreciate this formula, okay? But the goal, what I hope to convey is that here we have a very direct connection, more specifically to entanglement. And what this formula does is it geometrizes entanglement. So we have some understanding of entanglement in quantum field theories, and that understanding gets turned into geometry via AdS-CFT. Okay, so I hope to sort of convey some of the physics here in entanglement, and then how it gets geometrized by this formula. Okay? But as I said, there's a certain amount of background material we'll need first. And I think there's going to be some overlap with the other lectures. I know I wasn't here for Jai Kumar's first lecture yesterday, but I understand he covered entropy and so on, and Shannon entropy and so on. So, and some of what I say today will probably overlap with some of what he says today, but I think that that's probably fine. I also should say that you're absolutely welcome to interrupt me with questions at any time. For example, now. Maybe it's too soon for questions. Okay. So we're talking about entropy, and as you know, in quantum mechanics, entropy is quantified by the von Neumann entropy, or I should say, there is a von Neumann entropy, and this is a function of a density matrix, and the function is this, and it can be written as a Shannon entropy try to be consistent. Where rho A or pi are the eigenvalues of rho A. So we have the Shannon entropy. We have the von Neumann entropy, which is also the Shannon entropy of the eigenvalues of the density matrix. And what is it in quantum mechanics that this quantity quantifies? Well, of course, their entropy does a lot of different things. In classical mechanics, it quantifies the uncertainty, how much you don't know about the microstate of the system. And in quantum mechanics, it does that as well. And more generally, this notion of uncertainty in the state of a system is what gives rise to the state being mixed. So how mixed the state is measured by the von Neumann entropy. Let me just, as an aside, because this is just one of these technical points that comes up a lot in discussions, and so it's good to have seen it, even though I'm not going to spend a lot of time on it. So clearly from this, and as will be clear in the rest of the talks and so on, you already know entropy is a very important quantity, and we'll give many examples where we want to calculate it. And so it gives rise to the question of how you actually calculate it. And one of the beautiful things about this quantity, unlike many quantities in information theory, is that we often can calculate it. That's not something we should take for granted. Of course, how we calculate it depends on what we know and so on in the particular situation. But if you just imagine that somebody gives you a matrix, let's say it's some spin chain or something, and it's a 2 to the 100 by 2 to the 100 matrix, and then you want to compute this quantity. From this formula, it looks like you're going to have to diagonalize this matrix. And that is one way to do it, but that's very expensive. And if I have some more abstract presentation of a state or a density matrix, I may not know what its eigenvalues are. So there's a way around this, which goes by the name the replica trick. So I'm just throwing out buzzwords because they're important because they come back again and again. It's a way around having to actually diagonalize this matrix if the quantity you're interested in is this. So if you're not actually interested necessarily in all of the eigenvalues. And that is to compute this quantity. So this is the definition. This is the definition. So where alpha and this is called the Renyi entropy. And it shares many of the properties of the von Neumann entropy. You can see that there's some funny business when alpha goes to 0, when alpha goes to 1. So what we have is this statement, which you can prove by L'Hopital's rule. Okay? And the reason that this, there's a log here. The reason that this might seem like a kind of a random formula, unnecessarily complicated, but actually there's a reason for the 1 over 1 minus alpha, because when you take the limit alpha goes to 1, you would get trace of rho A, which we know is 1, log of that is 0, so that's not very interesting. But when you use L'Hopital's rule, what you need to do is take the first derivative with respect to alpha of this quantity, and that actually gives you precisely this. Okay? And why is this useful? Well, the reason is that S alpha, for integer alpha, S alpha is easier to compute because it's just the trace of a power of the density matrix. And so, for example, if you wanted to calculate trace rho squared, that should be, if you have a rho presented to you in almost any presentation, you should be able to compute trace rho squared, okay? And trace rho cubed, and so on. And if you can do that, then what you can show is that this is actually an analytic function of alpha. And so, it has a unique analytic continuation. There's a theorem about that. So if you know S alpha for all integer alphas, all positive integers greater than 1, we're trying to figure out what it is for alpha equals 1. So, but assume you know it for alpha equals 2, 3, 4, up to infinity, and assume you can figure out what the analytic function is that fits that data, fits those integer points, then you can evaluate the function you get at alpha equals 1, and that leads to this. Okay? And a setting where this is actually what you do in practice is when you compute these things by a path integral. So if you're doing a quantum field theory, and if your state is determined by some Euclidean path integral, maybe it's the vacuum state, maybe it's a thermal state, some other state that you prepare by Euclidean path integral, then trace rho squared is some other path integral. I mean, it's some kind of partition function on some manifold, some Euclidean manifold, and trace rho cubed and so on. So the job that you have is to compute a whole bunch of Euclidean path integrals on different manifolds. And if you're smart enough, you can do that. And then if you're even smarter, you can find the analytic function that fits the values of these partition functions you get. And you can take the limit alpha goes to 1. And that's how we often compute this in practice. Okay? That's how we get to the von Neumann entropy. Yeah, so basically the answer is yes. So for a given system, as I said, this is an analytic function, and on alpha greater than or equal to 1. And so if you compute it for alpha greater than 1, you can take the limit. Sometimes the systems we deal with are limits of systems. So an example is a very common, familiar example is a thermodynamic limit. And in a thermodynamic limit, various quantities are going to infinity, and including usually the entropy is going to infinity. It's scaling with the number of particles or the size of the system. And so then you might divide by the size of the system and try to take that limit. And now you've got an order of limits issue. And so if you first take the thermodynamic limit of the Renyi entropies or the Renyi entropy densities, there it's not guaranteed that that limit, the limit of an analytic function is not necessarily analytic. So you may lose that property. And you may in fact find that this function in that thermodynamic limit is not analytic anymore, that it has non-analyticities signaling phase transitions. That's very familiar from thermodynamics. So that will happen. And one reason why I'm spending a little bit of time answering this question is that when we get to AdS-CFT, in AdS-CFT, the classical limit on the gravity side is a thermodynamic limit, and so you get these non-analyticities, you get these phase transitions, and so on. So that phenomenon actually is relevant for the kinds of stuff we'll be talking about. But if you have a fixed finite system, for any fixed system, this is an analytic function, the same way that in statistical mechanics, the free energy is an analytic function of your parameters, of your chemical potentials. Okay, if you don't take a thermodynamic limit. Yes? Presumably because some limit was taken. I mean, so, another issue that happens in actually evaluating this, sometimes you'll assume that, so here, let's say alpha is 3, then you actually have 3 copies of your system. And then in evaluating this by some method, you may have to make some assumption, for example, that the symmetry among the 3 copies is preserved, okay? And if that's not true, then you'll not calculate it correctly. So there are examples where you have this replica symmetry breaking, which is a phenomenon which is more familiar maybe from spin glasses and so on, but can also occur in this setting. And so there are certainly subtleties that can occur. Okay. Yeah. So in fact, thanks. I was going to say that. So these are of interest in their own right, and I don't want to spend too much time on it. They have all kinds of very nice and interesting properties. But basically, they encode. If you do know this for all alpha, you can do an inverse Laplace transform to figure out what the PIs are. So it's just a way of encoding the moments of your eigenvalue distribution, but in a way that is maybe a little bit easier to calculate than actually diagonalizing a matrix. Okay, in the sense that you could say, well, haven't you basically diagonalized the matrix? But you haven't learned what the eigenvectors are. So this is a way of avoiding the problem of figuring out what the eigenvectors are. If you don't care what the eigenvectors are, this is much easier than actually diagonalizing the matrix. Okay. Any other questions about this? Okay. So so we have this notion of the von Neumann entropy. And in classical mechanics, entropy arises from uncertainty, from the fact that you can't necessarily know the microstate of your macroscopic system, et cetera. And in quantum mechanics, that's certainly also the case. But in quantum mechanics, you also have this other phenomenon that it doesn't occur in classical mechanics, which is entanglement. And so in particular, if you have a bipartite quantum system that's where there's entanglement present, then that entanglement will be reflected in the value of the entropy of one of the systems. Okay, so let me just, without going through all the theory, because I think Jayakumar is going to do that in the rest of his lectures. let me just assert that if we have a bipartite system, let me call it AB, and it's in a pure state, then first of all, you have this fact, which is not hard to prove, and this quantity quantifies the amount of entanglement. So for example, a bell pair I will probably, in much of the lectures, sort of set this log2 factor, which is slightly irritating conversion factor between the conventions of information theorists and conventions of physicists. So information theorists would put a log2 here as a way of counting the number of bits. And in physics, we're used to using a natural log. And so because of this clash of conventions, the formulas often get littered with these irritating log2 factors. And I'll sometimes just forget to write them. So it'll be up to you to figure out where the log2s should go. So this is the case when you have a bipartite pure state. But of course, the bipartite state could itself have been mixed. And in that case, this equation is no longer true necessarily. And furthermore, this statement is no longer true. So, so if rho AB is mixed, then these things are not necessarily true. So for example, they could be completely uncorrelated, in which case you could just have two systems that are totally uncorrelated with each other, in which case each one of them may have an entropy or may not have an entropy, and whatever entropies you might calculate, they might be equal, they might not be equal, but they certainly have nothing to do with the amount of entanglement. There's no entanglement between them. And so S of rho A and S of rho B tell you nothing about the amount of entanglement between them. And in fact, it's a difficult problem in general to figure out whether there is entanglement or not between two systems if they're not jointly in a pure state, which is something I'm not going to go into. Despite my claim that these lectures are about entanglement entropy, I'm actually not necessarily, I mean, we will talk about the distinction between entropies that come from entanglement and other entropies, but as we go along, but not all the entropies we talk about will be ones that come from entanglement.
Maybe it's a very basic question, but how does entanglement come up uncertainty in comparison to non-entanglement?
So in a state like this, if I ask what is the density matrix for A, so this is a state where AB is pure. So in this case, in fact, let me just write this out here. So rho AB is just this state. It's pure, it has zero entropy. But rho A, if you compute it, is this state. So if you only have access to A and you measure its state, half the time you'll get 0 and half the time you'll get 1. And in fact, in any basis at all, half the time you'll get one basis vector and half the time you'll get the other basis vector for any orthonormal basis. This is a maximally mixed state for a two-state system. And so it's uncertain. And of course, the point is that, I mean, this is a purely classical quantum phenomenon because in classical mechanics, if a joint system is in a definite state, every part is in a definite state. How can it happen in quantum mechanics if that's not true? The answer, as always in quantum mechanics, is the uncertainty principle. That's the difference between classical and quantum mechanics. And due to the uncertainty principle, even when your system is in a full state, is in a definite state, there will be some observables that are not, that do not have definite values. And in this case, any observable related to only A alone does not have definite values. The only observables that have definite values are ones that relate to A and B jointly. Okay, and so to know that the full system is in a pure state, you need to do measurements on A and B simultaneously. If you just do measurements on A, just do measurements on B, you will never know that jointly the system is in a pure state. Well, so this system, I mean, there are uncertainties. So there are observables that have a non-zero uncertainty for this state, right? In particular, any observable that is just depends on A alone, you would compute its expectation value with this density matrix, and it will have an uncertainty.
No, I'm just saying it also has an uncertainty.
Yeah.
So is there any way to quantify that uncertainty in terms of entropy? Because ornament entropy is 0. So is there any measure for quantifying the uncertainty for pure state?
Oh, okay. So, right. So if you get 0 for S of rho A, for the von Neumann entropy, for a single system, what you know is that system is in a pure state. That doesn't, of course, mean that when you make a measurement, you'll get a definite value. Okay? Because of the uncertainty principle, there are observables for which, even in a pure state, you will get an uncertainty. What this doesn't tell you anything about the pure state. It just tells you that it is in a pure state. Okay, so you have no idea if you just computed this, you have no idea what state it is. And the same goes even if this is not 0 and you find some value, you don't know anything about the actual eigenvectors of the density matrix. The eigenvectors of the density matrix are the states that make up the ensemble of states that define the density matrix. So this is just one number. It can't, it only tells you this one fact about the state. It doesn't tell you anything else about the state. Okay, and that's good and bad. But one reason it's good is that it kind of gives you a global picture of this state. Let me be more specific, actually, and go back to this thing. If rho AB is mixed, and let me give an example of the kind of thing that you can compute with this that gives you some partial information about the systems. Okay, so in general, regardless of whether rho AB is pure or mixed, so this is a general fact about von Neumann entropies, and here I'm going to switch to a notation. So you have a relation between these three quantities. And by this, I mean, I hope it's just tiresome to write the rows. Okay, so in a general joint state, rho AB, okay, this is going to be, there's some relation. Okay, so in particular, if A has a large amount of uncertainty and B also has a large amount of uncertainty, Sorry, yeah, if A has some amount of uncertainty and B has some amount of uncertainty, AB, the uncertainty of AB is bounded by this. In what way? Well, basically, so this cannot be more than the sum of these two. And it saturates, furthermore, when A and B are completely decorrelated. So if A and B are completely decorrelated, then the von Neumann entropy is extensive, which means that S of AB equals the sum. And that's the biggest it can possibly be. Okay? And this inequality is called subadditivity. And it's a key property of the von Neumann entropy. And just to link it back up to this, the Renyi entropy also is extensive because of the log. If you just work it out, you'll see that if rho AB is just rho A tensor rho B, so if A and B are completely decoupled from each other, if they're completely uncorrelated with each other, then the Renyi entropy for fixed alpha will add. So S2, so you have this, you have S2 of rho AB equals S2 of rho A plus S2 of rho B. However, it is not subadditive. So it is not true that when they are actually correlated, you can have states where this is actually, for let's say alpha equals 2, you can have states where this is actually larger than the sum of these two. Okay? And this kind of property is an example of why the von Neumann entropy is kind of the gold standard. Okay? It has a lot of properties that, let's say, Renyi entropies don't have. Okay? So you have this, and also you have S of AB. The equality case happens only if rho AB equals rho A tensor rho B. Okay, and that means that this difference, which Pawel mentioned in his talk yesterday, this is the mutual information. Okay, this is terrible board work. Quantifies the correlation. It doesn't, so an example, this Bell pair, well, we already computed S of A, S of B, and S of AB, and so we just get that I of AB is 2 log 2. Okay, another example, so this is example 1. Example 2 would be a classically correlated bits. Okay, so in that case, if A and B are perfectly correlated bits, then S of A is still log 2, S of B is still log 2, but S of AB is not 0 anymore. It's just log 2 because the pair of bits is either, let's say, 0 or 1, 50-50 chance. And so you don't get this, you just get half of it. Okay, so this is so entanglement is double the amount of correlation of classical correlation. Okay. Another important fact about these mutual information. Oh, I was going to write this. Is that if we have more than 2 systems, so if we have so for any row ABC, if you start calculating this for various unions, A, B, B, C, and so on, then you find this. Okay, so here we saw that if I give you a system A and it has some entropy, by adding a second system B, the entropy can go down. That can't happen in classical mechanics. So you might worry that now I have the systems A and B, they're correlated some amount. By some magic of quantum mechanics, by adding a system C, I can make that correlation disappear. So that maybe somehow A could be correlated with B, but uncorrelated with BC. Okay? So this is the question, can it happen? So I have my systems A, B, and C, that A is correlated with B, but it's uncorrelated with BC. And that would be obviously pretty weird, but you might worry about it because obviously weird stuff happens in quantum mechanics. We just saw a weird thing happen where where A is mixed, but by adding B, it's not mixed anymore. And this, you can breathe a sigh of relief that as far as correlation is concerned, that will never happen. If A is correlated with B, then it's correlated with BC. Okay? So this is, this one is called strong subadditivity. Additivity. And it can be written, if you write it out in terms of entropies, you get this complicated. Okay. Again, the Rennies do not obey any of this stuff, basically. Okay? So that's why the Renyi entropies, for the most part, are a means to an end. They're a means to calculate the von Neumann entropy. That's not to say they're not of some interest in their own right, but if you have the ability to compute the von Neumann entropy, you should compute the von Neumann entropy. Yes? Yeah, so for a classical system, this thing is bounded above by both of these. And so, although, let's see, sorry, I meant that it's bounded below, I'm sorry. For a classical system, of course, you still have this bound, but it's also bounded below by, let's say, S of A. Okay, so indeed, that gives you an upper bound on the, so for example, if you have two bits, they cannot, two classical bits cannot have a mutual information more than log 2. That's the largest amount of correlation there can be. Okay? It's always going to be the number, log 2 times the number of bits in the smaller system, if your system is just made up of a bunch of bits. Okay? Okay, two other things I want to say about this. One is that there's another inequality that goes the other way. Which is that S of AB is bounded below by the difference. And that shows in particular that if AB is in a pure state, then S of A equals S of B, which is something we already said over here. So this statement is a special case of that inequality over there. Another thing I want to say, so I've been talking about Bell pairs, is that, well, maybe I can write it over here actually. This statement, so this statement here, one way of saying this is that if you have, let's say you have many copies of the bipartite system in a pure state, okay? You can act separately. Okay, so this is sort of more of an operational or engineering viewpoint on all of this, where you're asking what you can achieve by doing certain operations, okay? And one of the kinds of things that you can try to do is you can try to make entangled states, or you can try to measure entangled states, and so on. And so entanglement is a resource, meaning that if you and I share parts of an entangled state, then we can achieve things using that. So we can achieve communications protocols, teleportation protocols, cryptography protocols, and so on. So entanglement is a resource from an engineering viewpoint. It's not a free resource because you have to make entanglement, okay? And in particular, if we're separated, if we can't act jointly, just as you can't discover whether you have entanglement without doing joint measurements, you can't create entanglement without doing joint operations, okay? So if we're in separate labs acting on our qubits, if the qubits are not entangled, there's nothing we can do to make them entangled. So in that sense, it's a scarce resource. It's not a free resource. And you can ask, well, let's say we do share some entangled systems, okay? And we want to make some bell pairs, okay? So we want to make some entangled pairs. Then the number of bell pairs we will be able to make is given by this quantity divided by log 2, okay? So you can make S of A over log 2 bell pairs. Okay, if in this situation. More precisely, you need to have many copies, and then what you're doing is you're acting on the many copies, okay, to make many copies of S of A over log 2 bell pairs. Okay, but roughly speaking, this tells you the number of bell pairs that you can turn your entangled shared state into by local operations. Okay, if you make non-local operations, you can do whatever you want. You can make as many bell pairs as you want. Okay, that's my lightning review. Yes. Right, that's exactly right. So this quantity doesn't really tell you whether it's a classical correlation or an entanglement. And in fact, there's actually no, when you talk about mixed states, there's actually no clean separation between between entanglement and classical correlation. So there's no single quantity that tells you this is, so let's say you've computed I of AB and you find that it's 73. Okay, so is that 73 because of classical correlation? Is it because of entanglements or some combination? So there's no clean way to say, well, the 73 is made of 50 units of entanglement and 23 units of classical correlation. And it's not because we don't know, or that notion doesn't actually exist when you're talking about mixed states. Okay, that separation between the two notions. And so there is a well-defined question, there is a well-defined yes or no question, whether there's any entanglement or no entanglement. And no entanglement, by definition, means that the state rho AB is some convex combination of states that are tensor products. Okay, so if you have a tensor product, rho AB is rho A tensor rho B, then of course there's no correlation at all. But maybe there's some 50% probability of one tensor product and 50% probability of another tensor product. That means that there is correlation, but that's not entanglement. Okay, so those states are called separable, and those by definition are not entangled. So a separable state is of this form, rho AB. So it's a convex combination of tensor products, and this and an entangled state by definition is one that's not separable. But beyond that yes or no question, there's no one way to quantify the amount of entanglement versus the amount of classical correlation. And that's a whole fascinating subject. If you give me a state rho AB, how do I know whether it's separable or not? And it's actually very hard. So this is not a product state. It is correlated, but it's only correlated classically. It contains no entanglement. This is how you would have written down a classically correlated state. You take a convex combination of product states.
How would an entangled state be?
It just wouldn't be writable this way. Well, so we have an example here. Of course, this is a pure state. So when you dig into the actual wave function, you see that the wave, it's correlated at the level of the wave function, as opposed to being correlated at the level of the density matrix. So if you have a bunch of possible entangled states and you take some convex combination of them, you might end up with an entangled state. Or you might not. So that's actually a very hard question in general. So the question is, what the difference between entanglement and classical correlation is whether the correlation occurs at the level of the wave function, like this, as opposed to occurring at the level of the density matrix. Yeah. That's right. So there's, one of the simplest tests for the presence of entanglement is just to take the difference between this and this. So if, let me actually write it down. So if S of AB is less than S of A, then they're entangled. So every state of this form will have S of AB greater than or equal to S of A. The difference here being the conditional entropy that I think was mentioned already in one of yesterday's lectures. Okay. All right. Any other questions before we, yeah? No. So if it could be entangled and yet obey the classical bound. It could be entangled and yet obey every classical property of von Neumann entropies. So the von Neumann entropies by themselves cannot necessarily tell you whether something is entangled. Okay. So let's say we are quantum field theorists or condensed matter physicists. Why would we care about this entropy, assuming we could compute it? Let me try to contextualize this in the setting of quantum field theory. Just why is this a concept that would even come up at all in quantum field theory? Well, the point is Einstein causality, which is one of the concepts that Alok taught us yesterday. And that tells us that in a quantum field theory, in a relativistic quantum field theory, spatially separated regions, the observables in them commute. And that basically says that these regions are different systems, or different subsystems, okay? So anytime you have multiple subsystems, I guess I erased my little cartoon. So if you have a system which is bipartite, I didn't define, by the way, what I meant by a bipartite system and so on. I just assumed that that's the familiar concept. And in fact, I'm gonna continue to be very weaselly about that because there are actually different ways in which you can have a bipartite system. And it gets subtle in quantum field theory, as I think we're gonna learn more about from the other lecturers. And so that's why I basically don't want to get into it. But what is true is that, I mean, one of the things you need, a necessary condition to talk about different subsystems, is that the observables in them should compute. Okay, so the A observables should commute with the B observables. So you should be able to simultaneously do a measurement on A and B. If you can't, they're not really, you really shouldn't think of them as different subsystems. Okay? And in quantum field theory, this happens. In quantum field theory, different spatial regions that are space-like separated, the observables in them commute. And therefore, they can be considered as different subsystems. And as soon as they're considered different subsystems, you should be filled with a burning desire to calculate entanglement entropies, right? Because that's what you do when you have subsystems, is you calculate in some state, like in the vacuum, let's say, or some other state, you can compute their entanglement entropies, okay? And I'm just gonna give you a bunch of examples that'll convince you that these entanglement entropies encode a lot of the physics that we're interested in quantum field theory, okay? So this is, the bipartition is our choice. And that's a good thing. So it means there's a lot of different things we can compute and write papers computing. You can write a paper computing it for this subregion and then write a paper computing it for a different subregion and so on. So it's a great thing that it's our choice. This is the Einstein causality postulate. And it's kind of a bedrock principle of relativistic quantum field theory. Meaning that, you know, some of those other axioms that we learned about yesterday, they get a little bit more complicated when it comes to like gauge theories or something. But this one, I think, is pretty safe, at least in a relativistic quantum field theory. Okay? And so that means that basically, crudely speaking, they have von Neumann entropies. Well, spatial regions. Yeah, okay, so, you know, what do you use to computing in a quantum field theory? Well, S-matrix elements, correlation functions, right? That's the textbook quantum field theory stuff you compute. And now it turns out you can compute this other class of things. And we'll talk about what you can learn from it, but just as an example, and something I meant to mention over here, I claim that this quantifies correlation. Of course, you guys already know a way to quantify correlation, which is correlation functions, obviously. So you can compute, given some observables, given some observable, an observable in A and an observable in B, you can compute this, and if this is non-zero, you know, then they're correlated. Again, this will not tell you whether it's classical correlation or entanglement, okay? So what is the relation between this and this? So this is one way to quantify correlation, this is another way to quantify correlation. And in fact, there's a bound, so this guy is actually bounded above by some formula by this. In particular, if this is zero, then they're definitely uncorrelated, which means that this is zero. However, it does not work the other way. So you can compute a correlation function, find that it's zero. That doesn't tell you the systems are uncorrelated. It just tells you that this particular variable is uncorrelated. Maybe there's some other variable that's correlated. If you compute it for every possible observable in A and in B, and you find it's always zero, then indeed you can conclude that they are uncorrelated, but you notice how much more work that is. This is one quantity versus an infinite number of quantities here. Okay? So this guy contains all correlation. That's the advantage of it. Okay? Nothing can hide from the mutual information. Whereas you can have some subtle form of correlation that is not observable that is not detectable by the first observable you might think of. Okay? And the same goes in quantum field theory, that all of these correlation functions we're used to computing may be zero. And in fact, there are quantum field theories like that that basically have no correlations of local observables. And yet they have correlation. Okay? And the way to detect that correlation, if you can do it, is by computing entanglement entropies and mutual information. Okay? So,
Question.
About the who? Okay. Can I postpone that? That's a very good question, which is directly related to this. But let me hold off on the Risch-Leiter theorem. But let me just say, well, as a partial answer, that these theories that have no local observables are topological field theories, which I don't think they really fall into the same category in terms of the axioms that we learned about yesterday. And so I'm not sure that the Risch-Leiter theorem would, actually it's an interesting question whether the Risch-Leiter theorem would actually apply in those cases. But still, you still have Einstein causality for those. You still have commutations. You still have observables. They're just not local observables. Yeah. Yes. Entanglement is a property of the state, whereas commutation of observables is a property of the system. So in fact, commutation of observables is a prerequisite to defining entanglement, right? The notion of entanglement presumes you have independent subsystems. If you don't have independent subsystems, then you don't really know what your Hilbert space is and so on, okay? So in order to define entanglement, you have to have independent subsystems. That means you have commutation, okay? And this is more general. So normally we would write things like, I was trying to avoid writing this equation, but I'll just write it and then erase it quickly. So in the simplest cases, your joint system is a tensor product. Okay, but in quantum field theories, it's not really true. It's more complicated, but you still have this, and so you still have a notion of mutual information and so on. Okay, so let's pretend we didn't see.
Can it so happen that your classical correlations and quantum correlations cancel?
They will never cancel in the mutual information because they both contribute positively to the mutual information. Yeah. So yeah, I don't think they would cancel. But as I said, there's no clean separation in a general mixed state of that there's this amount of correlation and this amount of entanglement. That notion is not really well defined. So here I'm talking, I mean, of course, the amount of correlation and the type of correlation depends on the state. I'm saying for a given state, there are many correlation functions, but there's only one mutual information for a given state. Of course, if you change the state, you change the amount of mutual information, you change everything. Right. Yeah. No, I would be in the vacuum. In that example, I would be computing the mutual information in the vacuum. Yeah. Yeah, you have to do an apples to apples comparison. So yeah. Yeah. Yeah.
Stressing how entanglement is a property of the state, not to be confused with operators. But in some other cases, we actually say, oh no, they are the operators. That would be algebraic quantum field theory, for example. We code in any way entanglement directly in the operators. So I think there's some terminology here that
Well,
systems that is part of the state. I'm not sure those up.
So in algebraic quantum field theory, you take as your primary thing the algebra of observables. And even there, given the theory, so the theory is encoded by the algebra of observables, basically, and then by GNS, you can write down a Hilbert space if you want, although you don't have to. But implicitly there's a state, which normally would be, let's say, the vacuum state. Okay, so so it's still, I mean, yeah, these things all depend on kind of what you're taking as your givens and what you're deriving from them. So in algebraic quantum field theory, you take the algebra of observables as your primary thing, and you kind of derive the Hilbert space from it. Okay, you build the Hilbert space up from, let's say, the vacuum, okay, by acting on the vacuum with all of your observables, okay? And I would say that it's in that state that you're computing these entropies. So it's still a property of the state, okay? So you could take, for example, the same algebra of observables and start with a different state, which would represent essentially a different superselection sector. You would end up with different entropies. So it's really not, it's something that ultimately really is, I mean, whether you say it this way or not, it is a property of the state. So as an example, let's say you want to do algebraic quantum field theory, but you do it, but you're interested in thermal physics, okay? So you write down as your correlation functions those of a thermal state. Then you have the same algebra of observables, but you would compute different entropies, okay? So it really is, you know, whether you say it like this or not, it really is a function of the state. Or rather, it's a function of both the system and the state. And I was sort of, when I was saying it's a function of the state, I was sort of taking the system as being fixed. Maybe that's the right way to answer your question, is that you could take a different point of view where you somehow take the state as being fixed and the algebra of observables as changing, and then indeed the entropy would depend on your algebra. So it's really a function of both. I mean, for me, it's part of the definition of a subsystem, of having independent subsystems, is that the observables commute.
So all bipartitions are not subsystems?
For me, they're kind of interchangeable, I guess.
The bipartition is our choice, so we can choose bipartition so that what they don't commute.
No. I would say, I mean, for me at least, that's like part of the, this very fancy diagram I drew, to me means what the content of this is that the A and the B observables commute. They can be simultaneously measured. I just wanted to emphasize that that is a fact about quantum field theories, and so we're going to everything is sort of based on that. Okay, so and let me be, you know, let's just draw a diagram to see what we're looking at. So we have some relativistic quantum field theory, and we're talking about spatial regions. Let's say in Minkowski space, so let's say this is and maybe we have some other dimensions too. Okay, so we have this. So what is a region or a subsystem in this setting? I should say, by the way, this is a very important point. So I am taking this as my starting point, which implies that all of the entanglement entropies we'll be computing are those of spatial regions. But of course, you can divide your quantum field theory up in other ways. You can factorize the Hilbert space in other ways. Okay, let me just give two examples. So maybe I have two interacting fields, phi and psi, and so that I have some action that it makes them interact, and I look at the vacuum. Then I could ask about the Hilbert space for the full field theory is the tensor product of the phi Hilbert space and the psi Hilbert space. And they're, in an interacting theory, they're going to be entangled with each other, and I can compute the amount of entanglement. Okay? Or I could say, I could work in momentum space. Okay? I could write the field in momentum space by a Fourier transform, and then I could talk about some part of momentum space, the degrees of freedom associated with some part of momentum space being entangled with those of another part of momentum space. Okay? So there's all kinds of different ways you can divide up a quantum field theory. That being said, to me, so why is it that 99% of the literature on entanglement entropies in quantum field theories and holography is this spatial subdivision, and only 1% is like that other stuff? And the reason is that this is absolutely fundamental to the definition of a quantum field theory. So here you're really getting at what makes a quantum field theory as opposed to just a quantum mechanical system. Okay? And that's going to be related to why there's a Ryu-Takayanagi formula for these spatial subregions, and there's no Ryu-Takayanagi formula, or at least it's very unclear. We're sort of, we don't really understand very well what's going on with these other kinds of ways of dividing up a quantum field theory. Not that that isn't interesting and may, someday we'll understand what's going on with that, but this is kind of the first thing to do when you have a quantum field theory. Okay. Okay, so what is a subsystem? What is a spatial region? Well, a spatial region, is a part of, let's say, of a Cauchy slice. So I have some Cauchy slice. This could be for any globally hyperbolic manifold, Lorentzian manifold, okay? And then I have a part of it. Okay? So if I have a different Cauchy slice, and then I write down a part of that, it's a different region. It's a different subsystem. You notice that I tried to draw it so that it looks like both of them are the same part of the x coordinate, let's say. Nonetheless, these are not the same subsystem because they're at different times. Okay? In particular, they're space-like related to different other subsystems. So why am I emphasizing? So first of all, if I were to do a Lorentz transformation, even though they subtend the same fraction of the x coordinate in this coordinate system, In a different coordinate system, that wouldn't be true anymore. Okay? But also there are other subsystems that, let's say A is independent of, the B is not independent of. Okay? So if I look at this, this is C. A and C are independent. Forget about what's happening here. So I shouldn't have made them touch. Sorry, that's like opening a can of worms. Okay. So A and C are independent because they're space-like related, but B and C are not independent. Okay? So you gotta be, this seems to suggest that you gotta be on the same Cauchy slice to define different subsystems. That's actually not quite true. So because you can have what looks like a different region that's actually the same. So if I have a different Cauchy slice that differs, let's say does like this. Let me get rid of C to avoid cluttering this. I need a different color. Say it again?
Just be outside the light cone. If another subregion is outside the light cone.
That's right. That's right. So the important thing is indeed the light cones. So that agrees with what I'm about to do, which is if I pick a different Cauchy slice, and I have some A prime here, so A and A prime are on different Cauchy slices, okay? But they have the same light cones, okay? And so that means that actually they are the same subsystem. So, and the way to diagnose that is to look at the causal domain. So if A and A prime have the same causal domain, then they're the same, then there's the same subsystem. So if D of A equals D of A prime, then A and A prime are the same subsystem. So here we actually, so we would quotient by this relation. Okay? Now, what's going on between A and A prime? That depends whether you prefer the Heisenberg picture or the Schrodinger picture. Normally in quantum field theory, you have the Heisenberg picture, and then the point is that the algebra of observables really lives on the whole causal domain. Okay? But if you prefer the Schrodinger picture, that's okay. In the Schrodinger picture, there's a state on A and there's a state on A prime, and they're not the same state. There's been some time evolution relating them. That time evolution is carried out by a unitary operator. So there's a unitary operator that maps the state on A to the state on A prime. And unitary operators don't change the von Neumann entropy. So they will have the same entropy. Okay? No, that's not true.
Cauchy slice. A is a flat slice.
Yeah.
And A prime is an arbitrary
Yeah.
slice with a non-trivial extension curvature. Then I think the dynamics will not be.
No, it'll still be unitary.
For the states, I think for the states it will be because you're going to like I mean the slice which is curved, the states are like Bogoliubov related to the slice. In general, I think people have shown that the pictures won't match when if you go from a flat slice to a curved slice.
But that'll still be a unitary.
On the Heisenberg, I mean the pictures, the Schrodinger picture.
Yeah. No, but even if there's a Bogolubov transformation relating them,
It's not Hilbert split, right? You can show that, yeah, you get, it's like, I mean, it's easy like that in the
between two Cauchy slices.
yeah.
Okay, I mean, this may be related to something funny going on at the corners here.
Okay.
But I think that globally, globally, okay, so let me just say that the story I just told about the maps here, indeed, or even to back up a little bit, the whole notion of having an entropy is a bit, per se, is a bit dodgy in quantum field theory for a reason that I'm about to explain, which is that actually it's infinite, okay? And it's a divergent quantity, it needs to be regulated, and once you regulate it, you spoil a lot of the properties that you're used to, so then what you do is you regulate it, then you calculate something, then you remove the regulator, maybe you renormalize in between, and so on. So there's all the messiness of quantum field theory, which actually makes the story a bit more complicated, and which I'm not really going to talk about very much, but in the context of algebraic quantum field theory where you don't regulate, where you're just working purely in the continuum, there it's more complicated and you don't really have this quantity defined. But morally you still have it, and you still have things like mutual information and so on. Okay? So this whole thing gets more complicated if you do it carefully, strictly in the continuum. Okay? So I'm going to be taking a more practical viewpoint where I regulate as we go along. Okay, but I think that's probably related to this issue. Okay. Okay, so now, what do we expect for S of A? Well, of course, it'll depend on the state, but very crudely, what we might expect. So let's say, for example, in a vacuum. So far, this is too abstract, right? I mean, it doesn't. This is just defining things. It doesn't tell you what kind of numbers you would expect to get. Okay, so to make it more concrete, let's maybe think like a condensed matter theorist and regulate the quantum field theory by maybe putting it on a lattice. Okay, and then maybe take the limit as the lattice spacing gets small. And so we have a lattice with, let's say, a local Hamiltonian. Okay, and then we take the subsystem to be some subset of the lattice points, okay? And we ask, what kind of entanglement do we expect between this subset and the other? So let's say at each lattice point, maybe I have a qubit, a spin, and then there's some Hamiltonian, which is a sum of products of nearest neighbors, some Ising thing or whatever, okay? And what do we expect for S of A in a case like this? Well, we might guess that the entanglement we get is due to the fact that we've separated nearest neighbors from each other. Okay, so in a system like this, if you're in the ground state of a local Hamiltonian, you would expect that there's some entanglement present between nearest neighbors. And maybe there's also some longer range entanglement there too. Okay, but you would certainly expect strong entanglement between nearest neighbors. And so you might expect the leading contribution to be given by the number of bonds that you've broken. Okay, so we've broken all of these bonds between nearest neighbors. And so this might be given roughly by the number of bonds connecting A and A complement. Okay? And this basically is given by the area of the boundary of A in units of the lattice spacing. Okay, so if this is d-dimensional, so if I have d-dimensional space, and if the lattice spacing is epsilon, and my region A, so I'm interested in making my region much larger than the lattice spacing, okay? Because what I want to do is I want to take a continuum limit, fixing my region, okay? So I want to imagine that I'm going to tune epsilon to be very small and keeping my region fixed, okay? So then this region is much larger than the lattice spacing, and so the number, and we want to make sure it's like relatively smooth on the scale of the lattice spacing. It's not doing some crazy zigzag on the scale of the lattice spacing, okay? So then the number of bonds broken here is given by the area of the boundary of A in units of the lattice spacing, okay? And the dimension of this surface is d minus 1, because I have a d-dimensional space. And so the area of a unit of lattice spacing is epsilon to the d minus 1, okay? So I get this kind of thing, okay? So this here is dA, the boundary of A, and this is called the entangling surface. Okay? And the only reason for going through this exercise is to hold on to this idea, because what this tells us already immediately is that from a quantum field theory viewpoint, this is, first of all, a UV divergent quantity, because this ultimately is some UV cutoff length scale. So S of A is a UV divergent quantity, but it's not as UV divergent as you might have thought. So there's a different UV divergent quantity that you can make given A, which is the volume of A in units of epsilon. So this is not equal to volume of A in units of epsilon. In fact, of course, it's much smaller. Okay? So if you believe this, what we've learned from this very simple analysis is that quantum field theories, so first of all, S of A is UV divergent, but we're not afraid of UV divergent quantities. We deal with them all the time in quantum field theory. But also, A is highly entangled with A complement, and also it's highly unentangled with A complement, by which I mean that compared to the amount of it, so it's highly entangled because I have a UV divergent entanglement entropy. By the way, I haven't justified that it's entanglement and not correlation, but let me do that right now, because we're in the vacuum, which is a pure state. Okay, so the whole system is in a pure state. So whatever S of A I find is due to entanglement. Okay, so it's highly entangled because I have a UV divergent amount of entanglement entropy. But compared to the maximum amount of entanglement you can have, then what is the maximum entanglement of entropy you can possibly have? I didn't write this down before, but I could have as another inequality. S of A, of course, is always less than or equal to log of the dimension of the Hilbert space of A. And what's the log of the dimension of the Hilbert space of A? Well, that thing is going like the volume of A, right? I have like a qubit or a spin at each lattice site. The number of lattice sites is the volume of A in units of the lattice spacing. And so what we're finding is that it's way less entangled than it could have been. Okay? I'm assuming here that maybe the whole system is infinite, or in any case is much larger than A. If you have a system where you're on a finite system and then A is most of the system, then it's really A complement that bounds the maximum possible entanglement entropy. Okay? But in any case, the point is that what we expect is the amount of entanglement is actually much smaller than it could have been. And that's a dynamical fact. It's due to the fact that I assumed that we have a local Hamiltonian, and so we guessed that the entanglement is mostly due to bonds being broken. Okay? I haven't really justified this, but this is what's seen if you do numerical calculations of entanglement entropy in spin systems. And I will justify it next time if one of the other lecturers doesn't beat me to it, which would be fine, by actually doing a computation of an entanglement entropy in a field theory, specifically in this example of Rindler space, which we saw yesterday. And in Rindler space, you can go ahead and you can compute the entanglement entropy. And so Rindler space is just where you take half of your system. Okay? And there, you can write down rho sub A explicitly, and then you can compute its entanglement entropy. And we will see that indeed it is proportional to the area of that entangling surface. Okay? But I heard something buzz, so I think I'll just ask if there are any more questions for today. So the entangling surface is the boundary of A. So in these pictures, it's just these points, but of course, if I was in higher dimensions, it would be, whatever the boundary of my region A is. That's the entangling surface. On the Cauchy slice. Yeah. So as a matter of terminology, if I'm in a d-dimensional space, then A is d-dimensional, and the entangling surface is d-1 dimensional, which is why I have epsilon to the d-1.
Why can't it be entangled with something outside the Cauchy?
So because those are not independent systems, right? So that's why, really the entangling surface is the boundary of the subsystem that you're talking about. And things that are on the same Cauchy slice but outside of A are things that it can be entangled with. Yes? Right, so at least in this cartoon, you would just get 2, and it would be independent of epsilon. That's a good point. So if D is 1, then you just have a chain, and then based on this analysis, you just get some number. And that's correct, at least in simple systems. But of course, it doesn't take into account the possibility of long-range entanglement. And there are certainly one-dimensional spin chains that have long-range entanglement for which it's not really constant. It's a little bit, it grows a little bit, it grows logarithmically. So you get a logarithmic enhancement of this picture. So this isn't necessarily completely true. As you might guess, often if you have a power that goes to 0, often it becomes a log, and that's what happens in this case. Yeah, that's a good example.
Any further questions?
Oh, yeah, I was going to mention that. Okay, so for what I'm talking about, I think for most of what I'm talking about, you can find references in my lecture notes. So I have lecture notes from 2019 called Introduction to Entanglement in Holography and Field Theory. And those lecture notes have relevant references. I may tomorrow and Thursday talk about things that go beyond what are in those lecture notes, and I'll try to give references then. Yeah. Yeah. Yeah, that's been studied a little bit, especially in work by Mark van Ramsdonk and his group, and Vijay Balasubramanian. So the answer is yes. I mean, there are universal terms there. And what you find is you can compute, for example, mutual information between momentum shells, between one shell in momentum space and another shell in momentum space. And what they do is, I mean, the whole notion of momentum space and shells in momentum space is an intrinsically perturbative phenomenon. And so they work in perturbation theory and compute the mutual information and find some general results there, which I don't remember off the top of my head. But it's important to understand that that is sort of a perturbative picture-dependent quantity that you're calculating. So, I mean, if you change your renormalization scheme, you will get different answers. If you work in a different perturbative picture, you'll get different answers and so on. So that picture of momentum space is kind of very tied to a particular perturbative scheme, where the stuff I'm talking about, while there is dependence on the cutoff on epsilon, in the end of the day, we'll compute things that are independent of epsilon. So it's sort of more, this is like more intrinsic to the field theory as opposed to a description of the field, a perturbative description of the field theory.
Okay, so if there are no further questions, let's thank Matt again.
Thanks.